All right, so chapter 6. First of all, let's start off with some definitions, okay? So a directed line segment is called a vector. A directed line segment is called a vector. And a vector, of course, has both magnitude and direction. We'll talk about what magnitude means in just a minute. They call it magnitude and direction. All right, so vectors, they're written a couple different ways. If they're in the book, they will be in bold. If you're writing it on paper, you want to write it like this. That's vector V. They always have an arrow on top of them, okay? So a vector that goes from point P to point Q looks like this, vector PQ. Okay, and it's not the same thing as vector QP. It's different from P to Q. So it depends on how long it is. So that's the magnitude. Magnitude is the length. And it also depends on which direction it's going. So the magnitude of a vector is, they write it like this. It looks like the absolute value, but that's to find the length of it. Okay? The old book had 2 lines, so if I ever write 2 lines on accident, it's because that's what I'm used to. Okay, so we could say that, or that's what the old book did. So if you ever see that, it's the same thing. Okay, it just means to find the length of it. Now, a vector in a plane, these are going to be just vectors that are on an XY axis. So let's say you have XY coordinate and you draw a vector in the plane, it would look like this. Has an endpoint, and I'm sorry, it has a starting point right here, and then it also has an endpoint. I know that looks like a ray, but that actually stops. Okay, that's the length of it. So the length of my vector is from here to here, and the direction of it is going that way. It's different than a vector that goes in the opposite direction or a different direction. Okay. All right, equal vectors. So if 2 vectors are equal to one another, then they have to have the same direction, and magnitude. So they're both going to point in the same way, and they're both going to be the same distance long. And then we call them equal vectors. So like, for example, if you had a vector, say up here, that looks like that, and you draw another vector that has the same length, it's going in the same direction, those are equal vectors. We're going to find a really easy way to see if 2 vectors are equal in just a minute. All right, so now we're going to talk about the component form of a vector. Sorry, everyone has that down? We're good? Same direction and magnitude. Component form of a vector is usually we're going to write a vector in its standard position. You know how when we did angles in trig, we always were in standard position. We're on the x-axis and we go counterclockwise. Okay, so standard position has the vector that has the initial point. Its initial point is at the origin. Its initial point is at the origin. Okay? All right, so we're going to graph the vectors RS and PQ, and then I'm going to show you how to write them in component form in just a minute. All right, so let's go over here and draw yourself a little XY plane, and we're going to graph vector RS. See how it's in bold on my paper? So I didn't need to put an arrow, but if I was going to write it like in my homework, I'd have to write RS with an arrow over it. So RS means that it's going from point R to point S, and that's our vector. So graph point R. R is at 1, 2. And then graph S, which is at 4, 4. Okay? So here's R, and here's S. And then it matters which way you're going. We're going from point R to point S, and we draw an arrow, and we stop right there. So that's vector RS. Now let's graph vector PQ. I'll do PQ in red. PQ starts at 0, so it starts at the origin, and then it goes, bless you, to 3, 2, which is right here. And that's PQ. My drawing's off a little bit. My spaces aren't the same. They actually are parallel. Are yours on your paper? They're better than mine? They should be. Okay, so let's talk about the component form of a vector. The component form is when you're going to start in your initial position, okay? And so let's say that this is how you find component form. See how P is at 0, 0? And Q is at, let's just say Q is at V1, comma V2. Okay? So I have P starting at the initial, at the origin, and then Q ending at V1, V2. Then the component form of vector PQ looks like this. Instead of parentheses, you're going to use a sharper edge, and it's going to be V1, V2. Okay? So for example, not over here, but over here. Let's say that I have a vector, I'm going to call it MN, and vector MN is -5, 7. Okay? All that means is you start at the origin and you plot the point -5, 7. So go 1, 2, 3, 4, 5, -5, 7's up here. And then you draw from the origin to that point, and that's vector MN. Okay? It all looks all fancy. It has these weird, I don't even know what these are even called. Do you know what those are called? I don't even know. They're not brackets. They're not parentheses. They're like Sharpies. I don't know what they are. But that tells you that this is a vector in component form, starts at 0, 0, goes out to -5, 7. Okay? Most of our vectors are going to be written like that. So let's write vector PQ up here in component form. So we're going to write vector PQ in component form. PQ would look like what? 3, 2. Okay? Starts at the origin. It goes out to 3, 2. So we can write it in its component form as 3, 2 with those sharp pointy things. All right, so now how do we get a vector in component form when it's not at the origin, like the vector RS? Thank you. What do we got? DK and Christian. Oh, we got a whole bunch of you. You guys all out on Friday, right? Here we go. So what happens when you're not at the origin? So for example, let's say that you have vector RS, and let's say R is given to you as the point x1, y1, and S is given to you as the point x2, y2. Okay, you can take any vector that's out in space, like out in the xy plane, you can bring it back to make it in its component form. It's very easy to do. This is what you do. I'll show you. To get vector RS into its component form, you're going to take x2 minus x1 and y2 minus y1. That's it. Okay? So what you do is you take its terminal point, terminal, and you subtract its initial. Okay? TI. I always call it TI, like your Texas Instruments. TI. Terminal minus initial. So let's do it. Let's go ahead and write our vector RS in component form. So this vector up here, still talking about this one, RS, where R is 1, 2, and S is 4, 4. So R is 1, 2, and S is 4, 4. And I'm going to write vector RS in its component form. And what do I get? I'm going to go terminal minus initial. So 4 minus 1, which is 3, and 4 minus 2, which is 2. And we've seen that before, okay? And so it says equal vectors right after. Vectors are equal if their component forms are equal. Component forms are equal. I don't know why I capitalized that, but I did. They're equal, okay? Component forms are equal. So vector RS and PQ, we can say that those are equal vectors because both of their component forms are 3, 2. And you know, when I drew it, I knew they were going to be equal because, you know, I've done this before. And when I drew it, they weren't. They didn't look equal. Did yours look equal?
Mine do.
Yeah? On my paper, they do. Like when I did it on paper. Look at that. That's really good. They look exactly the same length. They're going in the same direction. Okay, so direction and length. All right, next. Have you done all this before? No? Because I talked to Mr. Edlin yesterday, and he says you guys have done vectors and physics and stuff. Yeah? Okay. All right, now we're going to talk about, the magnitude. The magnitude of a vector is its length, right? And we go ahead and we call that, like if I wanted to find the magnitude of RS, I would do this. And it looks like the absolute value of RS, okay? Because it is. It's the absolute value of RS. It's the distance from here to here. Do you remember the distance formula? No. Ooh, someone had a program. Yo-chan, you do, right? No. Someone has a distance formula programmed into their calculator. It's pretty good. Ricky? Yeah, maybe it was. No, I don't know. Okay, anyways, so if you want to find the distance between 2 points, right? That's what this is, the distance between 2 points. You would go, the distance equals the square root. Do you remember how to do this? Yeah, x2 minus x1 squared plus y2 minus y1 squared. And where did we just see x2 minus x1 and y2 minus y1? Component form, right? So if something is in component form, then what you can do is to find its magnitude is you just take the square root of v1 squared plus v2 squared. That's it. It's component form. And that should make sense because guess what? When you're in component form, let's say you have a vector over here. Here's my vector, right? And let's say I want to find the distance of that. Isn't that just Pythagorean theorem? Here's A and here's B. And so this is the point AB, which its component form is AB as a vector. Isn't it just A squared plus B squared equals C squared? I'm trying to find this green distance right here. So there it is, right? It's all Pythagorean theorem. Like you think, we're going to get through these and it's like, oh, there's so much to memorize. There's not. Draw a picture and you'll see it. It's pretty easy. Okay, so here we go. Example. Yay, finally. Given the point that has initial point 4, -7 and terminal point -1, 5 of vector v, find the following. We're going to find its component form. We're going to find its magnitude, its length, or its distance, and then we're going to graph in component form. We're going to graph it. Okay? So first step, find the component form for vector v. So I'm going to say vector v is equal to, don't forget component form has these jaggedy things. They're not parentheses. And we're going to take the terminal minus the initial. Don't go the other way. That's going to be a different vector. So usually it's going to be, you know, the second number minus the first number. So -1 minus 4 is -5. And 5 minus -7 equals 12. All right, I'm going to graph this before I find its magnitude. So we're going to go to -5, 12, and we're going to graph this vector in its component form, which starts at the origin, just goes out to the point -5, 12. 1, 2, 3, 4, 5. Where's 12? It's about there. There we go. 12, -5. Look at 12. Got cheated there a little bit. That's okay. All right, so let's graph it, and you put your point way up here, and here's your vector. Nice straight line from the origin out to that point, and there it is. Okay? Now, I want to find the length of that vector. The length is its magnitude. So I'm looking for the magnitude of vector v, and if you ever forget the formula for it, you know, drop a perpendicular. This is just a right triangle. You've done so many right triangles in the past. This is -5, this is 12, and it's the old what triangle? The old 5, 12, 13. Yes, the 5, 12, 13. Let's say you don't know that. That's okay. You square -5, you add it to 12, you get 25 plus 144, the square root of 169 equals 13. So it has a magnitude of 13. That's its length. It's its absolute value. You know what absolute value is? Absolute value, like, yeah, it just makes everything positive. What's the absolute value of -5? 5. But absolute value is the distance from the origin, or distance from 0, which is a positive number. So the distance from here out to here is 13. All right, let's do another one. You want to try this one on your own? Yeah, you try it. I'll let you try this one. Okay, so I'm going to do it really quickly. Component form, you take initial minus terminal. So 4 minus negative 2, you have to be pretty good at subtracting negatives and stuff. And 0 minus 2 is negative 2. Perfect. Yay, 6, negative 2. You go over here and you graph it. 1, 2, 3, 4, 5, 6. Negative 2, it's over here in quadrant number 4. We're going to talk about its directional angle later. So that's when trig comes into play and unit circle is going to come back. Sorry. And then the magnitude would be the absolute value of this vector, which would be the square root of 6 squared plus negative 2 squared. You can just take the negative off because it's just going to be positive when you square it anyways. And you get 36 plus 4, which of course is 2 rad 10. Good job. Who got that? Yes. Yeah, pretty much everybody except for Yochan. All right, here we go. Vector operations. Part D. Vector operations are pretty basic. You have, addition and multiplication and scalar multiplication, stuff like that. Okay, so we've got scalar multiplication. Scalar multiplication just means multiplying a vector by a constant. I like that word scalar. It just sounds weird. So scalar multiplication, I love how they always call constants k, too. And what you do is you just take a constant and you multiply it times your vector. Now, if k is positive, then that means that you're just going to go in the same direction as v. Same direction as v. Whatever you started going in that direction, you multiply by a scalar that's positive, you're still going in that same direction. Okay? If k is less than 0, then you're going in the opposite direction. So a negative scalar makes you go in the other way, opposite direction. Okay. Vector addition is pretty good. Okay. They call it the parallelogram law. What happens is, let's say that you have a vector, let's call it vector u over here. Okay, here's vector u. They love to call vectors u and v, and people don't like u and v because their u's and v's look kind of the same. And then let's say that you have a different vector, and let's call it v, and v's over here. That's vector v. The parallelogram law says that you take those and you move one of them to the other one. So like we keep u where it's at, and then, and then we take vector v, and you can put v either on the tail or the initial or the terminal part of it. And so I can put v right here. And if I was going to take those two vectors and add them up, see, I could have also done v here, and then I could have also moved u over to here, and it makes a parallelogram. And what happens is, if you take u plus v, it ends up being the diagonal. It's called the resultant. It's the diagonal. All right, so this right here, this in red, is vector u plus vector v. It's the resultant, or it's also called the diagonal of the parallelogram. That's called the parallelogram law. Now, are you going to do that every time? No. The way that you're going to add up vectors is pretty easy. If you have vector u, and vector u is in component form, okay? We want all of our vectors to be in component form. We don't want them out in space. It's just weird. So vector u, let's say in component form, is a1, a2. And vector v in component form is b1, b2. Then we can take those two vectors and we can add them up. So you can do vector u plus vector v. And it's exactly what you think it's going to be. What do you think it's going to be? A1 plus b1, comma, a2 plus b2. That's how you add up two vectors. You take whatever's in the x spot of their points or whatever you want to call them, and you add them. And you take whatever's in the y's and you add those together too. Okay? And then a scalar, if you take a number, a constant, times a vector, what happens is you just distribute it in. You get k times a1 and k times a2. if I was going to take a constant times vector u. All right, next page. There we go. Ooh, we're running out of time. I've got to get to those unit vectors. It's important. Okay, ready? All right. Oh, there they are. Yeah. So the next one, we're given two vectors. We're given vector v in component form and vector w in component form. Find and sketch the following. So we're going to sketch 2 times v. 2 times v, what that does is it makes its distance twice as long. So you have vector v, and we're just going to double it, okay? So vector 2v is equal to, just take 2 and distribute it inside your vector and multiply both components of it. So 2 times negative 2 is negative 4. 2 times 5 is 10. So if they want me to graph vector 2v, I'd go to negative 4, 1, 2, 3, 4, and then positive 10. Here it is up here, and this would be vector 2v. I'm sorry, negative 4, 10. Yeah. Negative 2, 5, or it is vector 2v, but negative 2, 5 is also on here. It's right here. That's vector v, and do you see what that constant did? It just made it twice as long. In the same direction, too. Same direction. All right, let's graph, and let's find out what w minus v is, and then graph that. So w minus v would take w vector and subtract vector v from it. These are all going to be in component form. So here I would get 3 minus negative 2 is 5, and 4 minus 5 is negative 1. So there it is, 5, negative 1, and we can graph that vector. You don't have to graph w and v and find out what it is. It would be the resultant of vector w with the opposite direction of v would be there. That's diagonal in the parallelogram it makes. 1, 2, 3, 4, 5, negative 1, and that would be your result right there. Okay, pretty easy stuff, right? And then c would be then to take vector v, which is negative 2, 5, and add that to 3 times vector w. So 3 times vector w is 9, 12. Okay, so you multiply the scalar first, and then you want to add these up. So negative 2, 9 is 7, 5, 12 is 17. That's a lot of numbers. You can just estimate that. That's fine. Go like this. There's 7, and here's 17. And here's the vector. Okay? Pretty easy stuff, right? I feel like we're just adding and multiplying and subtracting. Nice and good. All right, and then there's one last part. Unit vectors. We also had a unit something. We had a unit circle. So unit vectors are going to be important because unit vectors are all going to go out. They're going to be 1 unit long, and so they're going to land where? On our unit circle. That's why they're so important. So unit vectors look like this. I'm going to call it vector u for unit. Unit vector, this is what you do. Let's say you have a vector v, and it's not a unit vector. That means it has a length that's either like 10 or 12 or 1/2. It could have a length of 1/2. What you do is you take the vector itself in its component form, and you divide it by its length. That's how you find a unit vector. Okay? Unit vectors are basically they look like this. Let's say we have a vector v, and let's say it looks like this. And I want to find vector v's unit vector. I take whatever the component is. This is in component form. Like let's say it's a, b. And I take that, and I'm trying to find the vector that's going in the same direction, but that vector is special because it lands on the unit circle. So I just take AB, let me see, green. I take that vector and I divide it by its magnitude, a squared plus b squared. And that'll give me the same vector or same direction. It just shortens my vector into a length of unit 1. All right, we have a couple of standard unit vectors, 2 of them. Do I need to slow down? Yeah? So you can catch up? No? You're good? Cool. We're doing okay on time, too. We have a couple of standard unit vectors. There's one called vector I. Okay? I hate the way that they label these. These are just what they are. If you get up into higher math, you know vectors I, and then you also have vector J. Right? It's like, why do I and J? This is not an imaginary I, this is vector I. Vector I is the standard vector that goes to 1, 0. Okay? Can you picture where vector I is? Vector I, I'll do it in green. I'll rewrite it in green. 1, 0. So it starts at the origin, and it goes out here to 1, 0. That's vector I. Vector J. Vector J is going to be, what do you think vector J is? You're smart. 0, 1. Yeah, you just switch them. 0, 1. So vector J would go along the y-axis instead. Okay, those are our standard unit vectors. We're going to learn that you can write any vector in vector I and j. So for example, if they gave you this vector, let's call it 3i plus 4j. Okay, that is a vector in ij form. Have you ever seen that before? Seen it in physics? No? Vector 3i plus 4j is the same thing in component form as vector 3, 4. Why do we need two ways to write it? I don't know. Which way do I like better? Which way do you like better? I like component form. It's just like there's i's and j's and a plus in the middle. But if you were to plug in 1, 0 for I and 0, 1 for j and add these up, you would get 3, 4. I could show you that, but I'm not going to do it. Okay, so here we go. We're going to find the unit vector of v, and then we're going to verify that it does have a length of 1. So vector v is a pretty long vector. It goes out there. It goes to 5, negative 5. How funny, I drew it wrong here. Oh, okay. So it goes to 5 and then negative 5. So it's over here, right? And that's definitely not a unit vector, because a unit vector only has a length of 1. But we're going to write this, we're going to find its unit vector. So its unit vector is to take 5, negative 5, and we're going to divide it by its magnitude. And the magnitude of this would be what? Ooh, you simplified it. All right, so it's the square root of 5 squared plus negative 5 squared. 7 minutes. And you get the square root of 50, which is, 5 rad 2. Very good. Who said that? Camden, was that you? 5 rad 2. Okay, so we want to simplify this. We want to simplify this vector. So this is equal to, and we're going to divide 5 rad 2 into both of these. So you get 5 over 5 rad 2, comma, negative 5 over 5 rad 2. So we're dividing it by a scalar. It's just scalar multiplication, really. And then we can simplify this some more. So we can reduce the 5s, and we get 1 over rad 2 and negative 1 over rad 2, which we then rationalize. Yes, do you recognize that? Rad 2 over 2 and negative rad 2 over 2. Of course it's going to be that. Do you kind of see that now? Because what is that angle right here? This right here is a 45-degree angle. And if I'm on the unit circle and that's pi over 4, haha, look it. There it is, my vector, rad 2 over 2, negative rad 2 over 2. Now, they ask you to verify that it has length 1. That just means they want you to take the square root of rad 2 over 2 squared plus negative rad 2 over 2 squared and tell me that that's equal to 1. But we know that, right? Because isn't sine squared plus cosine squared going to give us 1? Yes. All right, anyways, so then we get, I was all excited about that, no one else cared. We have rad 2 squared is just 2 over 4, and this becomes 2 over 4 also. which becomes 4 over 4, which is rad 1, which is 1. So it does have length 1. But we're like, of course it does. It's on the unit circle. We recognize it. Good one. Love that one. All right, one last one to go. That went all the way down my page. Did that go down your page too? Yeah, a little bit. Okay, last one. Find the unit vector of W and verify that it has length 1. All right, so V equals 2I. Let me show you 2 ways to do this problem. One is, if you don't like 2I, which a lot of people don't, 2I is the same thing as 2, and vector I is 1, 0. Okay? And this is just the same thing as writing the vector 2, 0. We want to find this guy's unit vector. So we're going to take its component form, divide it by its magnitude. Its magnitude would be the square root of 2 squared plus 0 squared, which is 2. So we get 2, 0, divided by the square root of 4, which is 2. And I'm going to divide both of them, and I get 1, 0. Okay, I didn't have to go through all that work. I want to show you that you can. But if I have a vector, and my vector is 2I, you know what 2I is? It's out here. What's my unit vector going to be? It's going to be, of course, it's going to be 1, 0, right? Sometimes drawing a picture might help you, and you go through all this work. You can do it that way. You learn the formulas, you do it. But this is just twice I. Vector I goes in this direction. It's twice as long. If I wanted to make it into a unit vector, then I need to just make it as the vector 1, 0. Or you can call it, oopsies, not J, you can call it vector I. And that would be an answer too. Yeah? W. Oh. Find the unit vector of V. Oopsies, typo. Thank you. Huh, it even has it on my page, typo. All right, didn't fix it though from last year. Okay, we're good.